So let us move on. Our next talk will be about future neutrino-less double beta decay search legend experiment presented by Frank Etzarts, if I'm correct in pronunciation. So Frank, 5 minutes before end of your talk, I will tell you. Okay?
Thanks a lot. Can you hear me okay?
Yeah, I hear. Please go ahead. Yeah.
Thank you so much for the nice introduction. And I would also like to thank the organizers for the invitation and for organizing such a wonderful conference. So it's a great pleasure for me to talk today about the future of neutrinoless double beta decay searches using germanium detectors. And the first thing I would like to do is to show you the agenda of my talk. So I will start with a very brief reminder of the physics of neutrinoless double beta decay. Then I will focus on the background mitigation strategies that we deploy, particularly in the case of Germanium 76. Then I will focus on our experiment, which is called Legend. And in the end, there will be a short summary. All right, so let's start with a short reminder on neutrinoless double beta decay. So actually, it turns out that single beta decay is energetically forbidden in some isotopes. And then the so-called two neutrino double beta decay becomes visible and is the only standard model allowed decay mode. So you can see a nice illustration of the process here. So basically we have this nucleus and within this nucleus, 2 neutrons are converted into 2 protons and 2 electrons, as well as 2 electron neutrinos are emitted. So this process has already been observed experimentally in several isotopes, and amongst them is germanium 76, where we focus on. Now, then there's also the hypothetical decay possible, which is called the neutrinoless double beta decay. And in this case, the decay is pretty similar to this one, but you can see here in the Feynman diagram, essentially we also have these 2 neutrons within 1 nucleus, which are converted into 2 protons. And then in the final state, we only have these 2 electrons. So we don't have the emission of any antineutrinos. And this is then the so-called neutrinoless double beta decay. Now, why is it interesting to search for neutrinoless double beta decay? So first, it tests theories with lepton number violating interactions. Namely, if we observe this decay, this would be a clear indication for lepton number violation by 2 units. Then it also sheds light on the nature of the neutrino, namely if the neutrino is its own antiparticle and therefore a Majorana particle or a Dirac particle on the other side. And finally, we can also obtain information about the neutrino mass scale by searching for this decay. And this is illustrated in this formula here. So by measuring basically the half-life of the decay, we can relate this to the effective Majorana mass, which is a coherent sum of the different neutrino mass eigenstates. Then we also have some other factors here in this formula. So we have the axial vector coupling constant, the nuclear matrix element, and the phase space factor. Now, what is the experimental signature of the decay? And you can see here the energy spectrum for the case of germanium 76. So we expect a peak at the Q beta beta value of the decay, which for germanium is at roughly 2 MeV. And this is due to the fact that basically, since we do not have any antineutrinos in the final state, we have a 2-body decay, and then we are looking for this peak here. And then we also have here below this peak the contribution of the 2 neutrino double beta decay, where we have this continuous energy spectrum. Now we are searching for this decay in germanium using germanium detectors. And why are we using them? So they have several distinct advantages. The first thing is that they have a very high detection efficiency, and this is due to the fact that the source is equal to the detector. Then for germanium detectors, the isotope enrichment from the natural abundance value of 7.7% to more than 92% is possible. Then another advantage is that germanium detectors have actually the best energy resolution of any neutrinoless double beta detecting technology, namely 0.1% at the Q beta beta value, so at this 2 MeV. And this translates into the full width half max of roughly 2.5 keV. And this is then also necessary to isolate the neutrinoless double beta decay from the 2 neutrino double beta decay continuum. Now, another advantage of this detection technology is that germanium detectors have a very high density, and this means that the topology of our neutrinoless double beta decay is basically point-like. So we expect this decay to occur at a very small volume of roughly 1 cubic millimeter within the detector. And it turns out that this is a very effective means of discriminating background events, which typically have another topology in the germanium crystal. So there are several other advantages. One is that the energy scale is very linear, and also germanium detectors allow for a stable and long-term operation with minimal maintenance. Okay, this already brings me to our experiment, which is called the Large Enriched Germanium Experiment for Neutrinoless Double Beta Decay, in short LEGEND. And here you can see a nice picture of one of the last in-person collaboration meetings last year. And there are actually quite a number of people involved. So we have roughly 47 institutions and 240 scientists from all over the world. And the mission statement of our collaboration is to develop a phased germanium-76 based double beta decay experimental program with a discovery potential at a half-life beyond 10 to the 28 years, using existing resources as appropriate to expedite physics results. So let me focus a bit more on our strategy. So I've already said that we want to combine the best features of previous experiments, in particular the germanium detector array experiment and the Majorana demonstrator experiment. And we also have inputs from other research groups and experiments. So on the one side, there was the very successful Gerda experiment, which was a neutrinoless double beta decay experiment for germanium-76 at Gran Sasso. You can see a nice picture here, and the advantages of Gerda were that they had a very efficient liquid argon veto system, so the bare detectors were operated in a liquid argon cryostat, and a low activity shield. So on the one side, Gerda, and on the other side, we have a US-based experiment also searching for the decay in germanium-76, which is called Majorana demonstrator. And here the major advantages are that they have very good low noise signal readout electronics and highly radio pure materials. So for example, you can see a sketch of one of the cryostats with the detectors, and this cryostat is made from ultra pure electroformed underground copper, so very pure. So combining the best of these technologies and other experiments, we then go to the LEGEND experiment, where we want to combine the lowest background of any neutrinoless double beta decay experiment that was achieved in the field by Gerda with a number of 5 × 10⁻⁴ counts per kV kilogram year, and the best energy resolution of any neutrinoless double beta decay experiment obtained by Majorana with 0.1% at the Q beta beta value of 2 MeV. All right, so let me focus a bit more on LEGEND. So we pursue a phased approach, and the first stage is the so-called LEGEND 200 experiment. So here we will use the existing Gerda infrastructure at Gran Sasso, and we'll upgrade the cryostat to operate 200 kilograms of germanium. And here the background goal is actually to be better than a factor of 2 to 3 compared to Gerda in numbers 2 × 10⁻⁴ counts per kV kilogram year. And we can also express this similarly in counts per full width of max ton year. And then the sensitivity goal on the decay half-life is 10 to the 27 years. So even though there is the pandemic now, we are still on track to start data taking next year. Then the final stage of LEGEND is called LEGEND 1000. And here we want to operate 1 ton of germanium in staged payloads. So you can see a nice illustration here. And here we want to reduce the background by another factor of 20 compared to the LEGEND 200 goal to a level of 1 × 10⁻⁵ counts per kV kilogram year, and a sensitivity of 10 to the 28 years. And currently the location for the experiment is being selected. Okay, let me tell you a bit more about the discovery potential of LEGEND. So here you can see the discovery sensitivity as a function of the exposure, which is basically the product of our detector mass and the operating time. And the current or former experiments are located somewhere over here, with the Gerda experiment 10 to 26 years, operated for 100 kilograms year here. Then with LEGEND 200 in the midterm, we want to go to a discovery sensitivity of 10 to the 27 years. by operating 200 kilograms for roughly 5 years. So we end up by an exposure of 1 ton a year. And then the final goal is to really cover here the inverted ordering band with legend 1 ton and achieving a half-life sensitivity of larger than 10 to the 28 years by operating 1 ton of germanium for roughly 10 years, so that we end up at 10 ton years of exposure. All right, so let me go back to Legend 200 a little bit. So I've already mentioned that the experiment will be located at LNGS in Italy. And here we have 3,500 meters of water equivalent rock overburden to shield muons. Then we will reuse the Gerda water tank with a modified clean room here on top. Here you can see a zoom into the cryostat. So we have a huge water tank, and then in the center we have a liquid argon tank with the detector strings. And here we will use some upgraded lock system, some new detector mounts, and also a new detector type in Legend 200. Then we will also improve the liquid argon scintillation light system. And finally, we deploy improved readout electronics and a new string layout in Legend 200. And I would like to draw your attention to a very nice poster on the readout electronics for Legend 200 by Valerio, and you can find the link here to the poster. All right, so let's talk a little bit about the background reduction strategy that we pursue in Legend 200. So for the beta-beta-like signal, I've already mentioned that we expect this single site event energy deposition in a very small volume of roughly 1 cubic millimeter. And then we need to separate this signal from backgrounds. So first we might have a gamma that deposits part of its energy in one detector and then in another one. And to discriminate this kind of background event, we deploy anti-coincidence cuts in all 3 experiments. Then we can discriminate cosmic muons by the Cherenkov light that is created here in the water tank. And then also we have some scintillation light here in our liquid argon volume that is then read out by the fibers here and some photomultiplier tubes. Then we have this liquid argon veto system. Again, if we have a gamma here within our liquid argon tank, it deposits part of its energy in the detector and then also creates some scintillation light in the liquid argon. We can read out this with a fiber system again, and then have a coincidence event and can very powerfully reject these kinds of events. Then we also deploy pulse shape discrimination techniques where we can discriminate, for example, gamma events that undergo multiple Compton scattering in the detector. So they have a very different signal topology compared to this single site energy event energy deposition. And we can also discriminate surface events from alpha and beta particles. Finally, in Legend 200, we will deploy some new detector holding structures made from a plastic material called Ben. And this also scintillates, so this is an additional means to discriminate these gammas. All right, so this is now the Legend 200 background model. So we did very sophisticated Monte Carlo studies based on experimental data and material assays as well. And here you can see the background budget for all the different anticipated components. And here the Legend 200 background goal is actually what I've already mentioned, this smaller 2 × 10⁻⁴ counts per kV per kilogram year. So this is here a factor of 2 to 3 better than what has been achieved in Gerda. And now if we sum up all these contributions, we actually end up somewhere over here at a value of roughly 1 × 10⁻⁴ counts per kV kilogram year. So this means that we can really achieve our background goal with Legend 200, which is very promising. I would also like to point out that here the largest single background components can be associated to surface background. So we have the potassium-42 beta decays, and then also some alpha emitters, which contribute most to the background. All right, and there will be a much more in-depth talk on this by Matthew Green on Friday in the neutrino physics session. All right, so how do we want to achieve this background reduction compared to Gerda-Majorana? So I've already said in the background model that we have shown the feasibility of reducing the backgrounds. using Gerda, Majorana, and other dedicated test stands. And here is a collection of the methods we deploy to achieve this goal. So first we have improved radio purity levels by deploying this electroform copper and ultra clean PTFE materials, which have been shown very successfully by Majorana. Then we deploy a novel detector type. I will focus on this in a couple of slides. We will use a purer liquid argon, so this increases then the scintillation light yield and the attenuation length. We also install in Legend 200 an improved scintillation light readout compared to Gerda. And as I've already said, we will use improved signal readout electronics. And finally, we use all this pulse shape discrimination analysis techniques to very powerfully reject background events. All right, so there are a couple of detector types we deploy in Legend 200. So the first two types are the so-called broad energy germanium detector. You can see a bisected view of the detector over here. And the P-type point contact detector, shortly PPC detector. So the patchy detector has been deployed intensively in Gerda and the PPC detector in Majorana demonstrator. And basically they are both point contact detectors, meaning that we have our readout electrode here in a very narrow region of the detector volume. And this leads to the fact that they have a very small detector capacitance, which directly translates into excellent energy resolution properties of these detectors. And in addition, we also have excellent pulse shape discrimination properties, so we can properly reject multi-site and surface events. So one drawback of this detector technology is that they only allow for relatively small masses, so 600 to 800 grams. And then if we want to build a large experiment, this in turn translates into the need for many channels and cables. So, and here comes the new detector geometry into play. It's called the inverted coaxial point contact detector, shortly ICPC. So with this technology, larger masses are possible from 1.5 to 2 kilograms. So that's 2 to 3 times the mass of PPC and patchy detectors. So here the advantage is that we then require less nearby parts. And at the same time, they have the advantages that also the PPC and patchy detectors have. So excellent energy resolution and excellent PSD capabilities. Now the detector type has another advantage, and this is that the surface to volume ratio is much lower. So this means that these detectors are way less sensitive to surface events. And there are much more detail on this detector type in these two publications. All right, I've mentioned in the background model that one of the most important components contributing to the background are actually surface backgrounds. And there we have two major backgrounds. So we have the beta decays, and the beta decays originate from argon 42, which is naturally abundant in the liquid argon. And this argon 42 decays to potassium 42, which in turn undergoes beta decay and produces electrons with 3.5 MeV. And now if the electrons are somehow, the energy is degraded, they can end up as a background in the region of interest at 2 MeV. And then we also have the possibility of alpha background events, mainly from polonium 210. So they roughly have 5 MeV. And again, if the energy of the alpha degrades, then they can end up in the region of interest as a background. Now, to investigate these surface effects in more detail, there are a bunch of different test stands that address these issues. And I would briefly like to show you the results of one test stand. So this is called the Galatea test facility at Max Planck Institute in Munich. So it's a fully automated setup which allows for a surface scan of the entire detector surface. And one peculiarity about this PPC type detector is that they have a large passivated surface. So this is the surface here on top, which separates our P plus contact, so the signal readout electrode, from the bias voltage electrode here on the mantle surface. And this surface is basically left floating, so at an undefined potential, and therefore it is subject to any kind of surface backgrounds and surface effects. And in preliminary measurements, we observed for alpha and beta particles that actually the energy degrades as a function of radius. So this can be seen here in this figure. Nevertheless, the alphas have a very distinct pulse shape so that we can very effectively reject these background events. Okay, so what is the current status of Legend 200? So the commissioning phase of the experiment has just started in Ransasso, and we did a first very successful test of the new electronics and DAQ and calibration system under realistic conditions, namely in the liquid argon environment. And we operated successfully some of the Gerda detectors as well as Majorana PPC detectors, and also for the first time this new detector type. And you can see a very nice calibration spectrum with the thorium source here for the different detector types. So what else is ongoing? So the detector fabrication from 2 suppliers has begun. And even though we have the pandemic at the moment, Legend is still on track to start data taking in 2021. All right, so then moving a step ahead with Legend 1 ton, we want to operate up to 1,000 kilograms of enriched germanium detectors in individual payloads. And here we want—
Sorry, 5 minutes.
Yeah, thank you so much. Thank you. So here we want to reduce our background even further by a factor of 20 compared to Legend 200 to a level of smaller than 1 × 10⁻⁵ counts per kV kilogram year. And how do we want to achieve this? So for the uranium and thorium background, we actually want to use, again, an optimized array spacing. We only want to deploy this new detector type, so these ICPC detectors. And then, of course, also want to use cleaner materials and so on. For the beta or surface backgrounds, we expect a strong suppression of this background by using underground argon. And then for the muons, we actually go deeper. So yeah, we can improve our shielding by going to a lab which has a higher depth. And then finally, this contribution of the surface alpha events can reduce significantly by not using this PPC type detector any longer. And here in the right figure, you can see an overview of our background model. And here again, also, this is very preliminary, but the background goal is expected to be met. All right, so this is the overall timeline of Legend. So the Gerda experiment has just finished data taking and was very successful and has just published the final results. Then the Majorana experiment is still ongoing and aims for an exposure of 75 kilogram years. Then for Legend 200, actually the purchase of the isotope is almost completed, and we are currently in the phase of fabricating the detectors. Then this is also currently ongoing, so we are currently installing the new lock, and the cryostat is being upgraded to be ready for Legend 200. Then the commissioning phase of Legend 200 will hopefully begin end of this year, early next year, and then we can finally start data taking somewhere next year. And here the exposure goal is this 1 ton a year by operating it for 5 to 7 years. And for Legend 1 ton, we are also working on this at the same time. So the ton scale down select process is currently ongoing, and then next year we actually start with the design of the experiment. And the earliest and optimistic Legend 1000 data taking time for starting data taking is then in 5 years from now. And this brings me to my summary. So Legend will search for neutrinoless double beta decay in the isotope Germanium-76 with an unprecedented precision. And we pursue this phased approach where we have the first stage called Legend 200, where we use the existing Gerda infrastructure at LNGS in Italy. The material and detector production is currently ongoing for Legend 200, and we did some very successful first electronics and DAQ tests in the cryostat, and the construction of Legend 200 will then start soon. Our overall background goal is to achieve this value 2 × 10⁻⁴ counts per kV kilogram year for a sensitivity of 10 to the 27 years on the decay half-life. And currently design studies for Legend 1000 are ongoing, and here the ultimate background goal is to reach this value smaller 1 × 10⁻⁵ counts per kV kilogram year with a sensitivity of larger than 10 to the 28 years on the decay half-life. And with this, I would like to thank you very much for your attention.
Thank you very much, Frank, for very detailed report about status and prospect of legend experiment. Questions for Frank, please? So may I ask you then, so you just your last slide, sensitivity for limit. What is your estimation for mass sensitivity?
Yeah, actually, I think I have a backup slide on this.
Yeah. Of course, we should assume some accuracy of nuclear matrix element calculation.
Yeah,
but anyway, can you say something about that?
Yes, of course.
Yeah.
So I've already shown this formula at the beginning of the talk. So basically, we can relate here our effective Majorana mass to the half-life on the decay by this formula. And then we have here the phase space factor, which is basically calculable. And we also have here the nuclear matrix element, which has large theoretical uncertainties. And now if we plug in all the numbers here, the GA and nuclear matrix element, we use these values here by Corraccio and Song. So this is relatively large range. And then if we plug in all the numbers and assume this value, which is actually the result obtained by Gerda, then we obtain this mass range from 80 to 180 millielectron volts. And likewise, we can also do this for Legend 200 and Legend Atom, for example.
Okay, thank you.
Okay, so I'm sorry, may I also?
Yeah, please.
To clear the question, because if you remember, it was earlier, how it's called, some announcement by Klapdor about observing before the Gerda in Moscow Heidelberg experiment of this zero neutrino decay. Yes, but now the question is closed completely. Yes.
Yeah. So I mean, the levels that I think the Klapdor claims there were 3, and they were on the order of 10 to the 24th, 10 to the 25 years on decay half-life. But now with the Gerda, with the most recent result, we are higher by this 10 to the 26 years. So this is basically completely ruled out.
Okay, thank you.
Yeah, of course.